The broadcast is now starting. All attendees are in listen-only mode.
Hey everyone, Cam here. On behalf of our whole team here at Odell, I want to thank you for joining another installment of Isolation Intelligence. Today we have Josh Gardner, the Vice President of Sales and Marketing at SpringAir Systems, and he's going to be taking us through the recent changes to the NFPA 96 standard, as well as showing us the proper design of grease hoods and how to maximize energy savings and reduce capital costs. Just a few housekeeping things before we get started. If you have any questions, you can ask questions in the questions box. Any questions that are asked during the presentation, we'll get to at the end. However, if you have one that's pertinent and that you want to ask within the context of what Josh is talking about, you can also raise your hand, and we'll try and get to those ones right away. You can also download a copy of the slideshow under handouts. And then, like with all of our webinars, you can watch a recording of this and download the handout on our website, which will be posted sometime tomorrow. So without further ado, let's get to it. Here's Josh Gardner. Go ahead, Josh.
Hey everyone, thanks for joining us today. As Cam said, here to walk you through commercial kitchen ventilation. SpringAir has been doing this for just over 30 years now, so we'd like to think we know what we're doing. I'm a little greener here. I've been with SpringAir coming up on 6 years now, but still, I think we've got a lot to offer. Just a quick note about me. This is what you saw, but what you didn't see in the rest of the picture is I've got a 2.5-year-old now who will probably be up for her nap in the next, I don't know, half hour or so. So you may hear her running around at some point. I've also got a dog that may occasionally bark, but hopefully it doesn't distract you too much. Quick agenda for the day is basically what Cam mentioned. We're going to go through some overviews for commercial kitchen ventilation, basic concepts, as well as some code updates and understanding. And then we're really going to dive into the meat of the presentation for me, which is what SpringAir really focuses on, which is maximizing energy savings, minimizing capital costs, and introducing new products, which we've been going at pretty, I think, hot and heavy for the past couple of years, and we'll continue to do into the next few. So commercial kitchen ventilation, what's the big deal with it? If you're familiar with it at all, you'll know there are a ton of codes around it, and that's because you're playing with grease. The commercial kitchen typically has lots of appliances that put off grease. A lot of them, such as fryers, have grease. And before some of these codes, and even after some of these codes, some of the more dangerous building fires originated in kitchens, just because it's such a big source of heat and flammable components. Once you've really capitalize on the safety piece, that's when we start talking about performance. So by performance, I'm talking about essentially removing all the odors, smoke, and effluent that comes off of cooking and putting it into the atmosphere, which is really, it's kind of the bare minimum hurdle when you're getting into the industry. Where we really focus is what I call the top of the triangle, which is energy efficiency. And so that means being able to do all the performance criteria with the lowest possible amount of energy, and that translates into capital costs sometimes as well. Just to give you a broad overview of codes and regulations, there's really 3 buckets that we look at. The first is NFPA 96. It's very focused just on fire safety. So they're talking about what materials hoods must be made out of, clearances to combustibles, non-combustibles, what exactly those materials are classified as, different construction methodologies. Does it have to be fully welded? Does it have to be seamless? Distances, cleaning, how often it should be cleaned, i.e. ductwork, that's something that has been updated as well. And then use, so how are you using the commercial kitchen ventilation system? The second main bucket we're looking at is ASHRAE. Most of you, as you are engineers, are well familiar with ASHRAE, but they're really an engineering organization, and they're not so focused on safety because that's really covered under NFPA 96, but they're more focused on specific applications, energy consumption, and then sequence of operation. So they are keeping people safe, but it's not just specifically, we don't want to burn down the place. It's more air quality, energy efficiency, things like that. The last main bucket to look at is UL and ETL. Those are listing organizations. We think of them as like a better housekeeping or good housekeeping seal of approval. Any inspector who's looking at a hood, if they see it's UL listed to UL 710 for hoods or 1978 for ductwork, is going to say this has been evaluated by UL or ETL, has been deemed to be safe and within adherence to NFPA 96. UL actually develops the standards and tests to them, whereas ETL only tests to standards. So that's the difference between UL and ETL, but there are some other things we'll talk about too. And the last, and really what I put the crown on there because they have the final word, and that's the AHJ. That's the authority having jurisdiction. So while all these other organizations put out codes and standards, the AHJ is really the ultimate interpreter and decision maker, and can look at their requirements uniquely. Most of them are pretty in line with what we view, but there are some that are more onerous than others, which we've worked with in the past. NFPA 96 in Ontario, so the new building code, they adopted it, I think 2 years ago now, but it's effective January 1st. They adopted NFPA 96 version 2014, so it's not even the most recent standard, but that's typically how standards are adopted. I'm sure everyone's aware of that. There are some new definitions of non-combusted and limited combustible materials. I'm not going to go through them in detail, but prior, they just said basically a hood has to be 3 inches from limited combustibles and 18 inches from combustible materials, and they could have zero clearance to non-combustible materials. But they did not provide a lot of specific detail around it, whereas now they do. Filters, there were some manufacturers selling hoods without listed filters, and there were also some service companies selling non-listed filters to be used in kitchen hoods. That is no longer permissible under NFPA 96. Another update is that any concealed portion of the grease duct must be leak tested. Many municipalities were doing this anyways, but it is now part of NFPA 96. So anyone who has adopted 2014 should be doing leak tests on concealed portion of ducts. Another thing was establishing a measurement system of grease deposits to know when to clean them. Previously, NFPA 96 had provided some guidance, which I would say was pretty good before, but as always, open to different interpretation. So they basically developed a system now where they measure the grease deposits to know exactly when that duct needs to be cleaned to provide guidance. All grease fans must be listed to the UL 762 standard. Again, most municipalities have been requiring that anyways. Upblast fans with the motor in the airstream. So just think about the mushroom type fans on the top of, call it 80 to 90% of restaurants. They need to be hinged to the curb. Again, most manufacturers were doing this because it's an access point for cleaning the duct. And the last bigger, it's not a huge change, but its thermal start is now a requirement. This is actually a really good thing in our viewpoint because one of the bigger issues you have with kitchens is if somebody doesn't turn on the exhaust system and starts cooking, that heat builds up in the hood and it triggers the fire suppression system. That's not a fun thing, it's not a cheap thing, and it's not a quick thing to clean up. So now, if there's heat in the hood, the exhaust system should start automatically. The last two, and these are, again, not huge issues. The fire suppression system must be brought up to code when really any change is made to the system. They specified and called out that cooking medium change. So if you have a fryer that you were cooking with vegetable oil and you switch to using animal fat, you are supposed to do the fire suppression. Most people should be doing that anyways, but now it's part of NFPA 96. If cooking equipment is replaced, even if it's like for like, the fire suppression should be got up to code. When the position of the cooking equipment has changed, which is a no-brainer, if you have a fryer nozzle over a tilt skillet, it's not going to be effective in extinguishing the fire. And then if the equipment is no longer supported by the manufacturer. So that's end of life stuff. We don't see it a lot because most manufacturers for kitchen equipment do a decent part of their business as parts sales. And then lastly, solid fuel has always been, and most people understand that solid fuel appliances need their own duct run. NFPA 96 now actually allows for some solid fuel equipment not to require its own duct run. However, it has to be very, very special, is what it says here. But it's unique. There's 11 requirements for it. Most of that is that the solid fuel is actually only used for a flavoring. So the solid fuel has to be below a gas burner. There's some other things like that, but again, that's something that can be gone through later. And most manufacturers who have equipment that complies with it actually state that clearly in their literature for their documents. ASHRAE 90.1 version 2013. This is what we call demand control. It's the statute, but basically it says any kitchen that has over 5,000 cubic feet per minute of exhaust needs to be compliant with ASHRAE 90.1, and that can be achieved in one of three ways. 50% of the fresh air is transfer air, so this is typically only useful in kitchens with very open concepts. The one thing we do see that actually can meet this a lot is grocery stores, where they have a kitchen operation where they're cooking take-home food. The second way to meet that is 75% of the exhaust must have demand ventilation with the minimum 50% modulation, and that again is typically the easiest, and that's why we call it the demand control statute. And then the last option is a listed energy recovery device with a minimum of 40% efficiency must be on at least 50% of the total exhaust. Again, when we look through all of those options, we do find that demand control is the most effective option and the cheapest way to get it to be compliant with ASHRAE 90.1. It does also, a side note on 90.1, it limits compensating hoods to 10% supply air, which we don't know anyone who can make a compensating hood be effective with 10% supply air. So it's basically meant that compensating hoods are no longer viable for commercial kitchen ventilation. Another part of ASHRAE 62.1, and this is kind of creeping through different municipalities are getting more stringent on it, but exhaust ducts passing through fire compartments must be negatively pressurized relative to the spaces they pass. Really good example for us is we did a steakhouse downtown Toronto. They had the ducts going up, I want to say it was 13 stories, and they were getting a lot of odor complaints from tenants throughout the building. When we actually measured the exhaust velocities at the filtration unit and then at the roof line, they were significantly different, i.e. there were a lot of holes in that ductwork. And so that's where we put they call it a booster fan on the exhaust outlet, so that the duct run was negatively pressurized, and that reduced the odor complaints, and everyone was happy. But that's one of the things you'll see later. We sell engineered grease duct, and that's one of the real reasons when we talk about that's all been tested and listed, whereas field fabricated ductwork is put together in the field. Listing agencies. We work mainly with UL, but we also do work with ETL on some things. UL is a really old organization, so they've been around since 1894. They work hand in hand with NFPA on almost all of their projects. There have been some disagreements over the years, but really, if it's in NFPA 96, chances are UL has a code and a standard written specifically for that with the reason. ETL is a newer player to the game, although now they've been in it for almost 25 years. They're much more globally focused, but they're gaining strength in North America. When they came in, they were very inexpensive to list products with. They've increased their prices over the years as UL has also been more aggressive in pricing, and they're it's nice to have two competitors in the field, to be honest. What's the difference between the two? UL develops and publishes standards and tests against them, whereas ETL, again, only tests against the established standards. Both are acceptable by almost all AHJs. I will tell you, I do feel that UL is more conservative and a better fit from a safety perspective, but there are very few municipalities who will not accept an ETL listed product. This is the AHJ. We talked about this already. They have the final say in everything. And then the adoption process we talked about, but it's a lengthy process. So the example is the NFPA 96 version 2014 was adopted 2 years ago in Ontario, but just effective January 1st, 2020. And again, that's the 2014 standard, so it's already 6 years old. The last thing I'd put is your mileage may vary. We've all had experiences with different inspectors that can be memorable. Most of the problems that we run into stem from two different sources. The first is different interpretation or application of code from another source. So some inspectors, depending on their level of experience, will try to apply a gas code or something that's not really specific to commercial kitchen ventilation to commercial kitchen ventilation. We've got a really good code department that we talk with inspectors on a regular basis, and when there's issues, we call them, we walk them through how we look at it, how the other parts of the industries look at it. We typically come to an agreement on what the move forward is. The last one, and we're seeing a lot of this now, is lack of understanding. Municipalities are, I would say, staffing up their inspection departments and building departments, and a lot of times they're really green people who are looking at, I mean, anyone who's read NFPA 96, it's not exactly a quick read, and there's a lot of detail in there, and you can get pretty confused in it if you don't understand how things are being applied. So that's where we just teach people as we go. So the basic principles of commercial kitchen ventilation: when we design a kitchen, everything starts with the appliances. We do that because technically, when you look at NFPA 96 or UL listings, they go by appliance temperature to determine air volume. We know that even though a oven is a 400-degree appliance and a range is a 400-degree appliance, they both output very different amounts of smoke and effluent. And so because of that, we always get the appliances to determine our air volumes. Based on the appliances, we design the hoods. We do everything in CAD and PDF, and it's all available really quickly. Typically, one of our reps can design a system in anywhere from 10 to 60 minutes, depending on the complexity of the project. Then you've got to get that grease out of the building. That's where the exhaust comes in. In this example, I've got a filtration unit on the end, but it could easily be just a mushroom fan. But anyone who's been working on this knows that if you're just exhausting a lot of air and not bringing anything in, you've got a really negative space. You're not going to be able to open doors, and things aren't going to work properly. So that's where the supply air comes in. And that's bringing in fresh air, tempering the fresh air in almost all cases. Certainly in Canada, it's going to be heated and in a lot of cases cooled to replace all that air that's being exhausted. So sizing supply units is one thing we get a lot of questions on. And it's really funny because a lot of people jump into code right away. But we like to jump into, hey, let's give you a quick understanding of things. Exhaust should always be greater than supply so that the cooking area is negatively pressurized. Just to understand this and compare it to some of the codes we'll look at in a minute, this helps contain cooking and prep odors so that they stay in the kitchen. If you're bringing in more supply than you're exhausting, that's pushing odors and smoke sometimes from the kitchen to other parts of the building, which is not a good idea. It also ensures hood performance and minimizes the chances of drafts. Obviously, just having a negative kitchen isn't going to eliminate drafts. You need to distribute the supply air evenly in order to do that. but it does minimize it. And then lastly, the greater the negative, the more the kitchen will draw from other spaces. So very negative kitchens will have some consequences, but we do see people going pretty negative on kitchens if they want to bring in, say, conditioned air from other spaces, because they're not conditioning the kitchen air. But heavy doors or open swinging doors are two of the things you'll see with a very negative kitchen. And then equipment that's in connected conditioned spaces may have a hard time keeping up with demand. So if you've got, call it a 35-degree day in Toronto, and your equipment for the dining area is sized for 30-degree days max, you're already going to be behind. But then if you've got a really negative kitchen, the exhaust is going to be pulling the conditioned air from the dining space, and you're going to have a really hard time keeping that to your target temperature. And so that's where we'll show you our typical guideline on supply sizing on the next page, but that's just one thing to keep in mind. So just looking specifically for direct fired makeup air units, this is from CSA B149, and it's when a direct fired makeup air is installed or ducted into a kitchen, it should be installed in accordance with the following procedure. So just based on us saying everything needs to be negative, but you don't want to be too negative, let's read these. So statute 1 says, of either normally closed or permanent openings, the total free area does not exceed 16 square feet. The direct fired makeup air shall be interlocked with a mechanical exhaust system, and the approved airflow capacity shall not be less than 90% of makeup air. So if exhaust is less than supply, that would be a positively pressured kitchen. So we're going to go ahead and say, let's not even really consider this scenario. The other thing that they're talking about, so basically if that kitchen doesn't have open area for air to come through, the direct fired makeup air unit needs to be no less than 100% and no more than 105% of the supply air. So 100% is neutrally balanced. 105% will be a negatively balanced kitchen because you're exhausting more than you're supplying. And that's really where we're looking at in terms of, if you want to use one number, what we typically say is size that makeup air at 95% of exhaust. That's going to meet all your codes. It's going to give you a negative kitchen, but it's not going to give you too negative kitchen. Obviously, this part here says it should be no less than 90% of makeup air. So theoretically, you could go to 120% of the supply on the exhaust, which would be 80%, depending on how you look at it. And that would be a negative. That's something we do see, but we don't always know the size of openings in the kitchens. So we typically default everything to 95% of exhaust when you're doing a direct fired makeup air unit. Direct fired makeup air units are the most common ones that we see. However, we are seeing more and more that are indirect. To touch quickly on that, the difference between direct fired and indirect fired. Direct fired makeup air units have a burner directly into the airstream, so you have products of combustion that are part of that airstream that are going into the kitchen, which is why they're a little, well, they are more tightly regulated, i.e. you need to be exhausting most of that out rather than pushing it into the space. Indirect units don't have an exposed flame or burner in the airstream, so they're heating in a different chamber and then transferring that heat into the airstream, typically through a heat exchanger, or sometimes you're using steam from a building steam system or cooling from a building cooling system. That allows you to almost do whatever you want with supply versus exhaust ratios. But again, you do need to have a negative kitchen. So for us, getting into what I've called the meat of the presentation is all about maximizing energy savings. We're going to walk through a two-step method for us because we find that this covers about 90%, 95% of the projects we work on. We do occasionally go to 3 steps, which is where we introduce heat recovery. But the cost to do that upfront, as well as the payback period that correlates with that, typically rules it out in most situations. So for us, we're looking at an example project, and again, starting with the appliances, we identify everything, get it put into the system, and then based on that, we design our hoods. So this is just a mock-up of the selection, dropped them into place. From that, we've got a KES unit. We could easily just size an exhaust fan as well. KES, sorry if I say so, is our exhaust filtration unit, or PCU. Some people call them scrubbers, whatever you have. It just cleans the air before it gets exhausted, removes the grease. Then we design a makeup air unit to bring that fresh air in. The last thing we typically look at is also engineered duct run. That provides a good quality product, typically saves some space versus field welders as well. The way that we're minimizing the exhaust volume is with our high efficiency hoods. So by minimizing the total exhaust volume as our first step, that allows us to typically find the cheapest energy savings with the quickest payback. Our Dynaflow hoods maximize efficiency by dividing supply air into 3 zones to balance the entire kitchen and exhausting appliances. The first zone is all about consistency. And those are diffusers at the front of the hood. They typically put out between 80 to 95% of the makeup air that's going in, just putting it into the room so it's consistently distributed so we don't have any drafts. The second and most important for a high efficiency hood is the capture and containment. This is actually an air curtain that blows down and slightly at an angle towards the appliances, so that as smoke rolls up into the hood, typically it's coming up along the back wall and it rolls back towards the top of the hood. That capture and containment air curtain pushes it back into the hood so it continues to roll as it's being extracted at lower volumes than a non-high efficiency hood. And lastly, we have something we call the comfort zone that's exclusive to us. I don't think any other manufacturers have it, but think of it like the vents on your car for heating and air conditioning. You can open and close them to get a little bit of fresh air down onto the chefs. It's not a huge amount of air, I will tell you that. Don't think that you're going to save everybody from being hot in the kitchen, but it will definitely cool them a little bit. From a Dynaflow perspective, one of the reasons we introduced a product called Revlo into the market probably 20 some years ago, and it was one of the first high efficiency hoods, but there were a number of things that made it challenging to work with in some applications, which is one of the reasons we launched Dynaflow, because it is very flexible, works in every application. There's not an application where you can say, oh, you know, we can't use Dynaflow because it won't fit, or the appliances won't work, the height won't work. It's just, it's so flexible. The way that the makeup air is done is we can actually tune it over each appliance. So we can open and close some dampers inside the hood to increase or decrease the amount of air curtain. And that's just because different appliances require different levels of an air curtain to be effectively captured. The mounting height, we mount everything all the way up to 87 inches above the finished floor. Most standard hoods are listed for anywhere between 78 to 80 inches above the finished floor. We listed ours a little higher because we find we have more and more requests to go higher. So just to compare our high efficiency Dynaflow hoods compared to what we call Ready Vent, which are straight filter hoods. So just the cheaper, you know, the cheap and cheerful, as cheap as you can get them kind of hoods. When we look at this same project, designed 2 ways, you'll see the exhaust volume drops from almost 8,000 to just over 5,000 CFM, so we've got a significant reduction there. The supply volume, because we're going at 95% of exhaust, corresponds with that. The duct collars, for us, we use the engineered duct on here, and because the version we used was round, we do have a square version as well, but that limits the amount, the size you have in the extractor. So we, on the non-high efficiency hood, we actually had to break this into 2 duct collars. Otherwise, we'd have to use it, I think it was a 26-inch duct collar, which wouldn't fit in the extractor, in the grease extractor. And then lastly, the common duct size difference between the two. For the Dynaflow hoods, you're looking at 24-inch diameter. For the non-high efficiency hoods, you're looking at a 30-inch diameter. That is important both in terms of the space that it takes up, but also in terms of the cost to put in the ductwork, and as well as fire wrapping that ductwork if it is in an area that needs to be fire wrapped. So when we look at high efficiency hoods, we calculate the energy savings. So our ready vent is the baseline. There's a little lower capital cost up front to do those, and we'll go through payback in a little bit. But the Dynaflow, just looking at the energy savings, between heating and cooling, we're going to be saving almost $8,000 a year. One of the things that we like to get from people as we're designing projects is all of the assumptions. We state these in everything so that everyone can poke, prod, question, change them if they want. But we got location. We use the ASHRAE data to populate degree days and everything based on that. Then operating hours, days a week, electricity costs, heating costs per million BTU, design temperature, and then the makeup air efficiency. So that's where we get everything. In our system, our reps can actually go in and print off energy savings documents that have all the calculations on. So you can look at your project and say, hey, does it make sense to go high efficiency, or should we just go cheap and cheerful in this case? So once we've done our work up front to minimize the total exhaust volume requirements, that's where we step in with demand control. And so now we're modulating the exhaust and supply based on the amount of cooking that's being done. And so the components we're adding here are temperature sensors in the duct collar, a central controller, and then demand dampers. So that's our zone flow dampers. It actually allows you to operate, I think we can do up to 16 hoods on one exhaust fan. And if only one set of appliances is cooking, that duct collar is open, wide open, the rest are closed, and that exhaust fan, or KES in this case, is probably only running at 10%, rather than running at 100% capacity and wasting all that energy, specifically with the makeup air. Makeup air is actually one of the biggest places where energy is saved, just because if you're exhausting less air, you're tempering less air coming in. So you're heating and cooling it less, which is one of the bigger costs for commercial kitchens. One of the reasons when we talk about commercial kitchens is that energy savings are so important is because typically in buildings, the kitchen is the #1 source of energy consumption, and kitchen ventilation is either #1 or #2, depending on the size of walk-in cooler and things that they've got going on. So it's an energy hog, and so we really try to take steps to minimize the energy consumption as best as possible. About our TrueFlow demand control system, I know that I think probably everyone here is Canadian. I'm actually dual citizen, but we got recognized by the US EPA, that's the Environmental Protection Agency, as a technology that saves a significant amount of energy versus traditional systems. The nice thing about TrueFlow is that savings come without behavior change. So because everything is based on how much cooking is going on at the time, you don't really need to make any behavior change. However, there is an ability for operators to look at the system, observe the system, and further improve or augment their energy savings. And that is really through the use of the control panel here. So they're looking at a simple visual cue. The bar has 3 colors. It can be either green, yellow, or red. And anytime you're in the red, that's not necessarily a problem, but it means you're using between 90 and 100% of your exhaust capacity. That's great. If it's, 1 o'clock, you've got your noon rush in, all the tables are full and you're cooking for everybody. But if it's, call it 10 in the morning and there's no one eating in the kitchen and all you're doing is prepping for the day, that means that you've probably got all your appliances on high. And believe it or not, some cooks will do that. They come into a kitchen, crank everything up. That's just how they start their day. But if you see it red and you're not actually cooking a lot of food, you should turn off some of your appliances or turn down some of the burners. Most charbroilers, fryers, everything have multiple burners so that you could turn down half of the equipment and effectively reduce your exhaust and energy consumption. All of our TrueFlow panels have the ability to tie in with BACnet. I say LAN, but we haven't done LAN in a long time because basically everyone's gone to BACnet now, and can be accessed through the internet if necessary. That is an additional feature. We don't build it onto many of ours because we do find that a lot of times people say, oh yeah, I'd like that feature. It's not utilized all that much, but it is a good thing to have. This is just basically an overview of different TrueFlow models. We've actually consolidated these, and I should update this. But we've really got, now we've got two versions, a TrueFlow with zone flow damper, so that's allowing you to put really as many hoods as you want on one exhaust fan, or a version without the zone flow dampers, and that's what we call TC. And they all have touch screens on now, and can all modulate pretty significantly to provide energy savings. So in this project, what we did was we specified TrueFlow Lite. And again here, so now we've got the heating and cooling savings, and that is, again, the same on both Dynaflow with regular control, so a big on-off switch, or with the demand control system. And this is where, because we're modulating here, we've got additional savings. We've got an algorithm in the system based on all the existing projects out there to show how much savings we're generating. But again, that's something, if you're designing with a rep and you have it's typically only in like commissary kitchens or institutions like hospitals where they have very regimented cooking schedules, where you can actually go in and say, okay, they're using this part of the day, this part of the day, or in some cases like commissary or big commercial places, it's cooking all day, not 24/7, but for both shifts where it's on. So we're going through and we can modify that. But as you can see, just based on having high efficiency hoods, you're at about $8,000 annual savings. By adding the demand control, you're moving up to about $15,000 annually. So it's a pretty significant investment, and where we really see that adding up is looking at capital costs. So when we talk to restaurant, whether it's owners or even universities putting in new kitchens, they always want to balance capital costs and energy savings. A lot of times everyone has this preconceived notion that long-term energy savings mean high upfront capital costs, but really when you look at it, we can actually provide a pretty good balance just by looking at the equipment and doing the project in a way that makes it meet both needs. So back to our example project here, as we look at it, these are capital costs. So just to buy hoods and control panel, which is ready vent, for us, you're looking at about $14,000 for a couple hoods and a control panel. When we go high efficiency, so these are the high efficiency hoods with, again, just a basic control panel, you've increased that cost by about 50%. So add another $7,000 onto that and you have high efficiency hoods. Now when you talk about adding in the control panel for a high efficiency package with demand control, you're seeing a bigger increase. So this is where a lot of times on the food service, you'll hear food service say, we can't afford demand control. It's ridiculously expensive. We don't want high efficiency hoods. Just give us the cheapest hoods you can get. Whereas on the engineering side, when we look at it, there's a lot of different inputs that you have to think about. So the size of the KES, pretty similar pricing here, just because we're using a cheaper version of the KES down here and a more full-featured one up here. And you've got VFDs up here, the makeup air, the supply air, same story, not too big of a difference. But here where we saw a really big difference was actually the ductwork. So because you were reducing that duct run size from 20, well, I forget, I could go back, but 24 inches to 20 inches, I think was the difference. You're actually saving significantly on the engineered duct run. So that you can have high efficiency hoods for no real increase in capital costs. To go to the demand control, yep, you've got a slight increase in capital costs, but when we go and look at what that means from an energy savings perspective, you'll see that that payback is actually pretty quick. Just a quick network. This is actually at the St. Jacobs Farmers Market. It's a really good looking installation, but it's a big open building, nice woodwork everywhere. They decided to go with the engineered ductwork, and it looks great. It's also UL tested and listed, and of a consistent quality. So the welds are all done by machine, not by humans on site, and everything's tested. So it's a really good quality product versus the field fabricated stuff, which is oftentimes good and acceptable, but we've seen it constantly where there are issues with field welded duct. Engineered duct also has greatly reduced slope requirements. So rather than the traditional 1/4 of an inch slope for field fabricated duct, you're actually only using a 0.5% slope. So it's a significant difference, especially if you're running over 75 feet, which is where field fabricated duct needs to have a very significant slope of 1 inch per foot, whereas engineered duct needs to only have 1/8 of an inch per foot. You also eliminate the need and the cost to wrap by using the zero clearance duct. It's also got, because it's round in the nature of it, improved static drainage and efficiency. So in some cases, you're seeing reduced horsepower on the fan or smaller fan sizing because you're using the engineered ductwork. So now as we go through, we compare equipment with the ReadyVent project. So that's the non-high efficiency. Your exhaust is 8,000 CFM. Your supply is just under 7,000 CFM. You've got what we call our KES 80, but it's maxed out. You've got no additional air volume or capacity in case that the static pressure was calculated incorrectly. The makeup air unit, you're in a what we call an SA18 unit, so there's no real difference there. But where you look at the true flow, this is another benefit. You're in a KES 60, but you're only using 5,100 CFM, so you've got plenty of capacity in case static is different than anticipated, or you just need to increase exhaust volume down the road. When you add true flow light, so the demand control, you're adding the VFD, which one of the benefits, sorry, excuse me, on our KES systems is you have the ability to extend filter life because you're actually increasing the speed of the fan to maintain the required exhaust volume. We find that that extends filter life by roughly 20%. And then lastly, capital costs as versus operating costs. So when we look at capital costs, again, we talked about these two being about the same, whereas with the demand control, it's more expensive. But when you look at annual savings and then look over a 10-year period, the payback on having high efficiency hoods, because you're saving money on the mechanical side, is actually negative. So it's slightly cheaper up front. When you add the demand control, it's an 11-month payback, which is pretty quick. We find most of our projects show between a 6 to 18-month payback versus competitive non-high efficiency projects. And then the last thing we really like to highlight is the 10-year savings numbers. So just by going high efficiency hoods, you'll probably be, you're in this situation, you're saving about $80,000, whereas with the demand control, that almost doubles the number to $135,000. So again, pretty significant savings. New products, which is a good portion of this presentation, but I know we're tight on time, so we'll go through pretty quickly. We solve problems at SpringAir. It's one of the things that I think where we make a lot of friends with whether it's engineers or contractors or food service consultants. We know that space is really at a premium, and a lot of times it's due to site conditions. So whether it's height restrictions, fire clearances, doors, or just unknowns, we know that less is more when it comes to being able to put equipment with tighter clearances. So based on that, we did a number of things in the past, I would say 12 months to our hoods, and got them all listed. The first thing we did is we zero clearanced most of our products. It does add 1 inch of size to the side that's needs zero clearance, but it can go right up against combustibles, and it's all UL listed. So it gives people a lot more real estate to just say, hey, yep, we don't care what that wall is made of. We've got zero clearance hoods, so it doesn't really matter. And then the second thing we did, on the previous slide, you'll note this has the demand control, the zone flow dampers on. Those take up about 12 inches on top of the hood. What we did was we actually engineered an internal zone flow damper that can go inside of the hood. And based on that, that allows us to get that headroom back up, but also to modulate all of the hoods so that, again, you can have multiple hoods on one exhaust fan. The next thing we've done, we've actually partnered with a company out of Denmark called Jimco. They're the originators of UV technology. And they're the ones who originally licensed the product to Halton, who's had the product in market for a long time. But they weren't satisfied with how that relationship has played out and wanted a new partner for their newest line of UV hoods. So we've got them listed. I think we've sold one or two so far, but we're just starting to talk to the engineering community about what makes us different. In case anyone is unfamiliar with UV, I just want to play this quick video.
Jimco Technologies has helped commercial kitchens with fat and grease removal and odor reduction for more than 20 years. Jimco systems are based on UVC and ozone technology that results in the cold incineration of organic matter from a process called photolytic oxidation. The process leaves no harmful residues. UVC light will split the fat and grease particles, which makes them more susceptible to ozone. The ozone will oxidize with the fragmented fat and grease particles. Photolytic oxidation will reduce pollution to the surroundings dramatically. It has been documented that Jimco's technology works and is the only kitchen pollution control system in the world that has an EU Environmental Technology Verification, ETV.
So that's a quick overview, but just before we go through kind of the details about it, anytime you're cooking with heat and food, you produce exhaust that's laden with aerosolized organic compounds. A 2001 study, this was actually in LA, where it was done, but they showed that meat cooking operations accounted for 21% of fine organic particulate matter that was released into the atmosphere. Again, that's in LA in 2001. Based on what we've seen as an increase in dining out, well, I should say prior to this whole COVID thing, the increase in dining out plus the increased efficiency in cars, automobiles, and other things like that, I would assume that number has gone up even more. There are thousands of organic compounds created during the cooking process. Looking through papers on this, it's kind of mind-boggling about the level of detail. People have looked at this, but the compounds have a really wide range of volatility and are responsible for both odors and pollution. And I'm sure everyone's read so many studies about air quality's impacts on life and long-term health. It's not one of those things where obviously when you look at NFPA 96, that's really looking at immediate safety, i.e., let's not burn down the building. Let's make sure everybody has a good dining experience. If there is a fire in the kitchen, it should be contained in the kitchen and extinguished in the kitchen, and the kitchen should be able to reopen relatively quickly. Everybody should be safe. This is more looking at long-term environmental concerns, and some jurisdictions are starting to take this more seriously. One example we're seeing is it's a charbroiler rule. I forget what the exact number is, but it's effective in New York City now and in a couple of the municipalities in California, which typically leads the way on environmental stuff. But anyone cooking meat with a charbroiler has to show that they're reducing particulate emissions by 70%. So again, that's one of the things we're starting to see this make more and more traction with the engineering community as well as municipalities. And so that's where, when we look at UV, we find a really good solution to reducing that particulate matter. When you look at current filtration technology in commercial kitchen ventilation, this is the one you see everywhere, and that's primary filtration. That's the filters that are in the hood. So in this case, we've got a hood with baffle filters. So baffles are the least efficient style of extraction, but because they're the cheapest, it's probably what you see on 80%, I'm going to say, of hoods that are in the market. It removes, depending on particulate size, which you're getting into a whole dissertation when you go too far on particulate size, you're removing about 40 to 50% of grease by volume with these. The secondary filtration units, which we've been selling for a long time, these are found between the hood and the discharge to the atmosphere. There's two main styles, mechanical filtration, which is what we do, which uses a set of media-based filters. Think about your furnace filter, call it on steroids, to remove 99.97% of grease from the exhaust stream prior to being exhausted into the atmosphere. The other thing we don't see in Canada almost at all, but is prevalent down in the US, is electrostatic precipitators. So these use a charged plate to basically knock the particles out of the air. The issue I have with these is that they lose their efficacy very quickly because as those particles are knocked out of the air, they land on that charged plate and reduce its ability to remove further particles out of the air. There are water wash systems in place for some units. They're also very heavy, but the efficacy thing is the thing that gets me hung up. Whereas the mechanical one, that filter is going to load and load and load. And as it's fully loaded, it's not going to be able to pull air through. And so that's where those filters have to be replaced in order for that unit to function properly. Again, we've got safeties built in and things like that, but I will tell you there's a way around everything. However, people would have to get really talented at rigging ours to be able to run without filters at this point. So that's where I prefer the media-based filters, the mechanical filtration, just in terms of they're always removing the grease from the air. And the last thing, and this is where we're getting into and we're starting to see others get into, is enhanced filtration. And these are filtration that go above and beyond current code and regulatory requirements. The two biggest ones you've seen or heard about are ozone and UV. And both have good and bad parts to them. We like to combine them both, which you'll see as we talk about, well, you heard it in the video too. But just to go through the UV filtration process, you heard it in the video, photolytic oxidation. So basically, what happens is the contaminated grease coming off the appliances with all of those aerosolized pollutants come through the UV system, and that's where UVC is the first step. So this is the bulbs emit a particular wavelength. I think it's 254 nanometer maybe, but it's UVC, and that actually breaks down the organic molecules. That does the heavy lifting for a lot of the removing the grease and odor particulate. But then as a byproduct of the UVC creation, oxygen is actually converted into ozone. That ozone actually combines with the remnants of the organic compounds and oxidizes them. And again, that's through ozonolysis. So, I mean, Jimco refers to it as cold incineration, but basically what's left is a white polymerized powder, and that either stays in the ductwork or gets exhausted into the atmosphere. But it's totally inert and doesn't have any negative side effects for anything. So the Jimco numbers, we'll go through them in a bit, but they're significant when you look at the reduction in both odors and grease. UV results, everything here on the top is with the UV and ozone system from SpringAir. On the bottom is without. So these are all taken at a restaurant that Jimco has been working with, well, not exclusively, but aggressively in Europe. You can think of them as having the golden archway into things. But this is a fryer duct up here that hasn't been cleaned for 60 months. Whereas this is a fryer duct that hasn't been cleaned for 12 months in the absence of a UV system. This is the hood cavity. This is actually the same time frames here, so that's 6 months and 6 months. But as you can say, the difference is totally night and day. It really is amazing. And we went and actually toured the facility here. They had a heat exchanger in the unit where we looked at, and they're changing the HEPA filter in the heat exchanger every 3 years. Whereas if they didn't have the UV system, I would assume that they would be changing it monthly, if not sooner, because those HEPA filters, grease really clogs them up pretty quickly. Lastly, this is an inspection hatch. This is 60 months and 12 months here. So you can see a very significant reduction in grease deposits inside the hood and ductwork. When we look at the benefits of UV, first and foremost, it's environmentally friendly. It's not a huge part of NFPA 96, but it's getting to be more and more important. And so we really like a product that is reducing grease and odor emissions. It increases the efficiency because filter boxes and fans are getting less grease on them. They're operating at more optimal conditions. Part of that is reduced maintenance, so less frequent duct and hood cleaning is required, and reduced filter consumption in media-based filtration units. We're working with Jimco right now to do a guaranteed reduction in filter consumption. I don't know what the exact number is going to be, but we're probably going to be using roughly 1/5 of the media, as long as we've got the properly sized UV system. Reduced risk of fire. We don't see it in North America, but in Europe, they've actually been able to work with underwriters to reduce insurance rates based on the reduced risk of fire. So why choose SpringAir? There have been UV hoods in the system for a long time. I'll be honest, I wasn't a huge fan of them for a long time because they do require proper maintenance, and there wasn't a good solution in the market to different appliances. Some of the appliances, like a charbroiler, is really hot and it has a lot of effluent. Heat makes UV less effective at breaking things down, and there just really wasn't enough UV in the hood to be able to properly do it. We're partnering with Jimco, who again has been doing it for 20 years. It is the only independently certified UV system, and so the numbers that they test, and the ETV did this on a wide range of applications, but the grease reduction was 50 to 85%, so very significant. And then odors were 44 to 91% decrease in odors, so that's really significant numbers. We are also, I don't know if anyone here is familiar with kind of the SpringAir approach. We always start with appliances, as I mentioned before. None of the other manufacturers that use UV use anything other than one standard frame size, which I say frame, but essentially it's the number of bulbs and the wattage in the bulbs in the hood, so they just do it based on linear feet of hood. We're doing it in concert with guidance from Jimco based on appliances. So if you've got a charbroiler, we're putting in way more bulbs and way higher wattage than if you've just got ovens or tilt skillets, things like that. And then lastly, the reduced filter gloss guarantee, which details will be shared with that in the future. They're not quite ready yet, just because we've got to do some further testing. So I think we've went through a significant amount of stuff today. I know I feel like I've done a lot. There are a lot of variables to go through, and that's really why we're here. We've covered a lot of ground. There are a lot of options. We typically push for energy efficient solutions, but what matters to us most is happy customers. And when we talk customers, it's not really just the people who are buying the equipment, it's the engineers, it's the contractors, it's our reps. We want to make everything easy. That's why we work with CAD, we spec everything, provide drawings and quotes in the same day, really, typically, and move on. So now I guess we'll do any questions, comments, or nasty remarks.
Thanks, Josh. So we do have a couple questions here. I believe Nate answered the first one. It was about the zone flow dampers, whether they're installed in the field by the contractor or factory installed on the duct collar.
Yep.
And then the next one is, can you visit the cost comparisons between engineered duct and field welded duct? So the next person asked the same question and actually posted an example. How much, assuming a straight run, should a team of 2 be able to install engineered duct at a 12-foot high ceiling, and how much cheaper would it be versus the welded grease duct?
So honestly, on a straight run, in terms of installation time, the first time you install the engineered duct, it's probably going to take you half the time of a guy to field weld it. And that's because you're learning a lot. After that, it goes together so quick. And typically, we're looking at about a quarter of the time, so a quarter of the man hours in field on installation. And a straight run, my guess is you're going to save 25%. Well, sorry, I should caveat that. If it's a straight run that needs to be fire wrapped, you're going to save 25%. The numbers on just bare duct, so just engineered duct that's single wall, it's about the same cost, we find, but it is a listed product, which is hugely beneficial. Where we find that, I'll be candid, field welded is more advantageous is if there are a ton of elbows and a really wonky ductwork system. The engineered ductwork pieces, elbows, Ys, Ts like that, are expensive. And so that's where field welded. When guys do the field welded stuff, they typically do linear foot and then a set cost for elbows. And so that's where field welded can be pretty competitive against the engineered stuff, if not a little bit cheaper. The one thing we do find is that there are a lot of GCs who will look at, okay, the engineered duct is this, okay, we can save some money on insulation, the field welded cost is that, but they don't look at the wrapping costs, because a lot of times they'll have an insulator come after and just wrap the parts that need to be specifically insulated because they're closer to combustibles. So it's, I think typically we're about 20% cheaper than field welded if it's fire wrapped. And I think we've got examples that show that.
Okay, and another question here. Permits generally require engineered drawings at submittal, but the drawings haven't been tendered, so hood supplier and mechanical trade haven't been selected. Does this mean SpringAir will provide the design upfront and risk not getting the job?
Oh yeah, all the time. I mean, that's we as much as we're a manufacturer, I would say, and actually, I mean, based on our headcount and when we look at staffing, we have a significant investment in IT, and so that allows reps to design and do stuff in CAD in a really short amount of time. And so that means they're entering appliance lineup and clicking a few buttons and getting full CAD drawings, for full PDF drawings ready to go that they can share. So there's not really an investment or a cost in doing that.
Okay, and I think that's it. If anybody has any more questions and wants to send them to myself or to Josh or to Nathan, we can make sure that they get to the right people and make sure that the answer from Josh gets back to you. I want to thank you, Josh, on behalf of the Odell team for coming and doing this presentation. And I want to thank everybody who is watching. Stay tuned for more installments of Isolation Intelligence. We have another one coming up on Wednesday. Again, like all of our presentations, you can watch the recording on our website. It will be up tomorrow afternoon at the latest, along with the handout that was here, which is the PDF of the lecture slides. And yeah, thanks again. Thanks, Josh.
Thank you. Thanks.